part 3. Okay, concave mirrors continued. We're going to take a look at the mathematical aspects as well as a couple of situations with concave mirrors. So we'll start off with the mathematical part. All right, and this will include the equations that are on your reference table, where they come from, sort of, and stuff like that. And so you really only have two equations for this unit. So the first equation is 1 over f, or 1 over your focal length, is equal to 1 over si plus 1 over so, right? Si is your distance of the image. And so is the distance of the object. And both of those are with respect to the point where the principal axis intersects the mirror, or the furthest point of the mirror. So this point right here. All right. Some people call them DO. In our case, we call it SO instead of DI is SI. It's just what our reference table uses. All right, and SO is the distance, again, of the object, and SI is the distance of the image, and your 1 over F, or F in this case, is just your focal length. All right, any of these on the reflective side, okay, the reflective side will be positive. And the non-reflective side is going to be negative. All right, that's just a kind of general definition. And so this will tell us, more or less in general, all the problems that we need to solve. The other equation that's given is the magnitude of the magnification. So just the amount it's magnified. And this is your image height, so HI, over your original height. Right, so how much larger it's gotten. And of course, this is the magnitude. They also give you the image distance over the original distance. And so this will tell you how much larger or smaller the object is. And so if m is greater than 1, okay, the image is larger than the object. If m equals 1, the image is the same size. And if m is less than 1, the image is smaller. All right, so let's take a look at a problem. So what we have is a concave mirror. Okay, we have an object that's placed 58 centimeters in front of the mirror. The object is 12 centimeters tall, and the focal length is 12 centimeters away. We want to find the location of the image by drawing the ray diagram, and we want to know the height and orientation of the image. So first, let's start with actually drawing where the image is going to be. So you're going to have to grab your ruler. Go ahead and change my ruler up. And so remember, there's a couple different drawings that we can do. The first one, okay, is just the parallel axis, or rather the ray that's parallel to the axis. And then if you recall, if it's parallel to the axis, that means it will go back through the focal point. Okay, you want to make sure you line your ruler up correctly. Neatness counts with these. All right, and so we have our incoming ray, and then we have our outgoing ray. Second one we want to do, okay, or that you can do, is when it goes through the focal point. If it goes through the focal point, it'll come back parallel to the axis. And so this intersection right here is where our image will form. And so what you want to do is take a ruler and you draw in neat as you can your image. All right, again, there are a couple other ones that you can draw in. For example, you could go through C, okay, and as long as you line up everything correctly, which is a challenge to do, it should go right through the same point. As you can see, if you're not neat, it doesn't. Okay, the other one you can do, you can also do the perfect, not perfect, but the reflection through the center. So the angle that this comes in at, if the ruler draws it correctly, right, when it hits this point, it should leave at the same angle. Okay, and it should also go right through. I'll use black, that way we can see. It should also go right through that point. So that's one that I had left off on the last video, but that's another one that you can do. There's really 4 that you can draw. Normally 2 will suffice. And so we should see a couple things. One, okay, the object is smaller. Or not the object, rather, the image is smaller. So we expect an m less than 1. The image is closer. Okay, so it should be the SI. Okay, this is our SO. SI should be less than SO. And there we go, we can start solving. So if we go ahead and start solving, 1 over the focal length is going to be equal to 1 over the image distance plus 1 over the object's distance. And so F in this case is 18 centimeters. So 1 over 18 centimeters. And since all the units are in centimeters, we could leave it in centimeters. Okay, we want to figure out the image distance plus 1 over 58. So if you solve this, you should give you a second to do that. SI should work out to be 26.1 centimeters. Okay, remember you're going to have to do an inverse in here. Do it with a fraction, add it over, take an inverse of the answer, right? And then you should be good to go. All right, the second part, we want to know what the magnification is, or rather the height of the image. Okay, and so we know that M is equal to HI over HO, but it's also equal to SI over SO. And of course, this is all magnitudes. That's how our reference table defines it. And so we can look at HI over HO equals SI over SO. And so the image height is what we want. The original height we know is 12 centimeters. Equal to, we know our new image distance, 26.1 centimeters. We know the original distance, 58 centimeters. All right, and if you take a second to solve that, okay, the image height is going to work out to be, or the magnitude rather of the image height is going to work out to be 5.4 centimeters. Okay, so it's smaller than the original height. Now the actual image height is equal to negative 5.4 centimeters. Now why is that? If you look, right, this is in the positive, this is going to be the negative. It's below the principal axis, and therefore it's negative. In this course, we can talk about the magnitudes if they want specifics. You can look at your ray diagram. Okay, you can always sketch a ray diagram. It does not hurt. All right, so let's take a look at two more interesting cases that should help you get through what you need to get through. And so here's the first one. Now I know nothing is on there, but let's go ahead and let's draw in an arrow that is at our focal point. All right, because this is going to give us an interesting situation, right? Because if it's at our focal point, that stops us from using the focal point as a point that we can draw through. However, it doesn't stop everything. So one thing we can do is we can draw our parallel ray. It's going to hit our image, and then, or rather, it's going to hit our mirror, and then that will travel back through the focal point. Okay, now we're kind of stuck here because we can't draw through C. Okay, or can we? Right? Technically, light will come off of our diagram, or rather of our object. And so we can line up our object with C, and we can still draw it through C, extending up to the mirror. Now you'll notice that the mirror in this drawing in particular doesn't, our ray doesn't hit the mirror, but this is what would happen. It would go that way and then travel through here, and this one will go this way and travel through here. And now there's one more that we can do. As stated earlier in the video, we can simply go through the center as long as you know what the angle is. Okay, and as long as you are neat. So it goes to the center. According to this, our angle is 32 degrees. So I'm going to go ahead and flip this the other way to 32 degrees. And go right off that center mark. And now you'll notice something. All of these rays, okay, this one, and this one, are all parallel. So no image is formed. Well, that's strange. So if you are at the focal point of a converging mirror, you're not going to get any image to form. These all come out parallel. If we look at it mathematically, that actually makes sense, though, because 1 over f is equal to 1 over si plus 1 over s naught. And if s naught, okay, or sorry, if your object distance is equal to f, then si has to equal 0. Okay, implying that no image is formed. Kind of interesting. All right, and then we have one more interesting case, and it's the case where what if we are actually in front of the focal point? Okay, what if our arrow is per se here? Just throw an arrowhead on this for us so we know. All right, so what if our arrow is there? Well, let's follow the same rules. Okay, the first rule is that a parallel ray will go in and then reflect through F. Okay, this is ray number 1. And I'm going to use 3 different colors for this one. Ray number 2, all right, we can go through the center for this one. All right, that's reading 50 degrees. So we can go ahead and make this also 50 degrees and go off. As you see, we start to run into an issue. This sort of looks like the same thing before, but the rays aren't quite parallel this time. And so we can do our last one, whereas we go from C to the arrowhead, right? Because it's going to reflect right off it. Get our angle correct. That should work, and we'll do blue for this one. All right, so it'll go this way and reflect off. Now, this one is different from the other one because if you look, these and these are diverging. All right, which means we're not going to get an image on this side, but we may actually get an image on the other side. All right, because remember, if you're standing over here, it'll look like the light is coming from inside this mirror, which again, we know is not true. However, we can visualize, okay, where this is coming from if we use our ray extensions. So I'm going to extend this purple. I'll use a dotted line for the extension. And I'll extend the red. And I'll extend the blue. All right, so you can see that I was a bit sloppy here. My angle here is probably off, okay? But there is an intersection point that happens right up here. So let's go ahead and we'll get rid of this purple one just to clear up what we're looking at. All right, and what we'll also do is we will extend our principal axis. Okay, we want this line nice and long. And what you'll see here is if we go to that intersection point, which is roughly here, all right, we get an image that is much larger. Larger image. It's upright. And it is real or virtual? Okay, correct. It is virtual because it's on the opposite side of this mirror. Okay, the non-reflective side. And so you've actually you've seen these before. These are like makeup mirrors. So if you get inside the focal length of a makeup mirror, it's actually going to magnify your face. If you're far enough away from one of these mirrors, what you see is all the images are actually flipped. Okay, so as you get closer to this mirror, okay, your image will be flipped, it'll be real. Once you hit the focal point, then your image will be non-existent. And then once you're inside the focal point, that's when you're going to have larger, upright, and virtual. So in this case, our objects, or our object, okay, S0 or S object is positive. However, our image's distance, right, it's going to wind up being negative. It's on the other side of the glass. And so when you're doing your mathematics for this, you're going to wind up using a negative for that. All right, catch you next time.